this is a strategic review of per unit system. There are multiple steps that are involved in per unit system. Obviously, in the reference handbook, they haven't laid it out like this, but they've provided you every equation that you arguably need in order to solve the per unit problems. So the most important thing when it comes to per unit systems is selection of base values. S base, voltage base. Once you have these two quantities, if you're working with a single phase system, then it's not line to line, it's line to neutral. But once you have the S base and the V base setup, calculating the Z base is a piece of cake, calculating the I base is a piece of cake, right? And then the relationship between the Z actual, right, is equal to so Z per unit is equal to Z actual divided by Z base. So Z actual is equal to Z per unit times Z base, right? So once you have the base quantities figured out, you've done the per unit analysis, and then you figure out the per unit quantities, calculating the actual values are not difficult. So in my observation, based on my experience working with tons of students, most of the mistakes, if not all the mistakes, are actually made here. Okay. Within the on-demand content, we worked through a stepwise process for selecting the S base. The first thing is that if the voltage base and the power base are given in the problem statement, you stick with that. All right. If they are not provided to you, then it is up to you because the actual values are not going to change. The only thing that's going to change is the per unit value. For S base, some of the guidelines are that they tend to be in the power of 10, right? So 1 MVA, 10 MVA, 100 MVA, and so on. Another good approach would be to select the equipment on the SLD which has the highest MVA rating, right? Those are some of the tips for the S base. For the V base, if the problem statement is explicitly giving you the zone voltage for even one zone, and we earlier did a problem related to that, then you use that as the zone voltage for that zone, and then transformers turns ratios are going to help you figure out the zone voltages in the other zones. Okay. And once you have these two, then figuring out the rest is pretty simple and straightforward. So be very, very intentional and methodical with per unit analysis and take the stepwise approach. There are a few other formulas and interesting concepts related to per unit. For example, if you have a transformer with a nameplate rating, this example I gave in the on-demand as well, 1 MVA, 13.8 kV, 480 volt transformer, and it has a Z% listed on it, right, on the nameplate. So that Z% applies to both the primary and the secondary, but the actual value is going to be different. The actual ohmic value, Z ohm, right, on the primary is not equal to the Z ohm unless they have the same turns ratio on the secondary, correct? But the Z% for both of them will be the same. And the reason over here is that the difference is in voltage. Now, when I use this transformer on a different system where I selected not 13.8 kV, but let's say 20 kV in the zone on the primary of the transformer, right? Then even the Z base for the transformer will not be the same. I will have to come up with a new Z base for the transformer because the zone voltage on the primary of the transformer is no longer 13.8. And this is the formula that helps us do that. You don't need to memorize this formula. You just need to understand the concept. That when you take an equipment and install it in a power system, where for calculation purposes, you have selected different values, and the difference can also be induced due to MVA change. So if I end up selecting the S base for the entire network as 2 MVA instead of 1 MVA, then even I have to do this base change formula. And they may not be very explicit about this step. This is a connection that you yourself will have to make. Okay? Does it make sense? So this is also a key point that you need to understand when it comes to the per unit systems. And as I've been mentioning all along, per unit system, three-phase and symmetrical components are extremely important because standalone, they make good questions, okay? But they form as like a foundational layer or multiple layers for more abstract advanced concepts than when we hit section number 3, induction synchronous machines transformers, when we hit section number 4, when we're talking about fault analysis, even transmission line modeling, power system stability, power flow, and protection, right? So they are sort of prerequisite pieces of information that you need to know when you're dealing with those topics, advanced topics, okay, in section 3 and section number 4. That's why we need to pay extra attention to per unit system. Make sure you go through all of the on-demand lectures on this, right? The multi-part lecture series, the quizzes. Make sure you go through the steps in the problem. Don't just brush off a seemingly, extraordinary step or something that is not obvious, that's not clicking. There's probably some reason why I solved it in a certain way, right? And make sure you understand it. Similarly with the homework assignments, multiple variations of these types of scenarios, and they are all designed thoughtfully to help you hammer these concepts down. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.